Hi, this is TW Huang. Today, I'm going to talk about Taskflow, a general-purpose task parallel programming system. This is a project to help you parallelize your applications in C++. This is what I am going to do for today's talk. First of all, we are going to understand the importance of task parallel programming. Then, I will introduce Taskflow and show you how we can use Taskflow to program static task graph parallelism and dynamic task graph parallelism. Next, I will showcase some real-world applications of Taskflow and conclude the talk. You probably already know parallel computing has advanced many of our application performance to a new level that is previously out of reach. For example, if you want to train a machine learning model with 40 CPUs, you can get 10x speed up. With one more GPU, you can bring another 10x speed up. More importantly, modern hardware has been designed to run in parallel for performance. For example, here I am showing you an Intel Haswell microarchitecture, which was released in 2013. This architecture typically comes with 4 CPU cores and has an integrated GPU. It is based on the superscalar architecture that can issue and complete multiple independent instructions per cycle. It also supports hyper-threading technology that allows a single physical CPU core to appear as 2 logical processors to the operating system. So, if you don't do parallel programming, you are not utilizing your hardware efficiently. However, today's parallel computing problems are very complicated and irregular. Here, I am showing you a computational task graph of a GPU parallel circuit simulation workload. The task graph models a GPU operation as an asynchronous task and the dependency between 2 GPU operations in an edge. This computational task graph can be very large. In this example, where we are simulating an NVIDIA deep learning accelerator design of 500 million gates, it has more than 1,000 asynchronous kernel tasks and dependencies. Even with a GPU, it still takes several hours to finish. This is another example of irregular parallel computing problem, where we want to parallelize the VLSI static timing analysis algorithm using many core CPUs. The analysis algorithm is modeled as a task graph that propagates the timing values from the input of the circuit to its output. For large design, the resulting task graph can contain more than 100 million tasks and 150 million dependencies. And it turns out parallelizing this type of irregular problem is not very easy because you have to deal with a lot of technical details such as parallelism abstraction, concurrency control, scheduling efficiencies, and so on and so forth. And there is always this trade-off between what you want and the cost of that intent. For example, everybody wants simple, maintainable, extensible, and portable implementation, but each of them come at the cost of performance. So, we want a solution that can sit on top to help us manage these details as much as possible, because programmers really care how fast they can get things done. By fast, I mean both performance and productivity. Among various solutions, task parallel programming, or TPP, is particularly effective for parallelizing irregular workloads. This is because TPP captures developers' intention in decomposing an algorithm into a top-down task graph, while delegating difficult scheduling details such as load balancing and concurrency control to an optimized runtime. And that is why, over the past few years, we are seeing a growing number of parallel programming libraries moving towards task parallelism, such as OpenMP's task dependency clauses, C++26 execution control library, TPP flow graph, and so on and so forth. Now, I'm going to introduce our TPP solution, Taskflow, and show you how we can use it to program static task graph parallelism. Taskflow is a general-purpose task parallel programming system that helps you easily parallelize your applications using modern C++. Let's take a look at an example in Taskflow. Suppose you want to do 4 things, A, B, C, and D. Each represents a function or a task. A runs before B and C, and D runs after B and C. To get a parallel execution for this task graph, you only need about 15 lines of C++ code in Taskflow. First, you define a task flow and executor. Then, you define 4 tasks in terms of C++ lambda function objects, A, B, C, and D. And then you use the precede and succeed methods to relate the dependencies among A, B, C, and D. When the graph is constructed, you submit it to the executor for execution. We call this model static task graph programming, or STGP, because the construction and execution of the task graph are separate from each other. You have to define the task graph first, and then you submit it to the executor for execution. A key innovation that distinguishes Taskflow from existing libraries is our Control Taskflow Graph Programming Model, or CTFG. CTFG goes beyond the limitations of traditional direct acidic graph-based model that does not allow you to perform in-graph control flow. With CTFG, you can create a condition task that returns an integer value indicating the next task to run. So you can perform if-else conditional tasking or iterative control flow that keeps running a subgraph until the condition is met. This powerful feature enables very efficient overlap among tasks alongside control flow. For example, here I have a task flow graph with 3 condition tasks. Condition task number 1 and 3 implement iterative control flow, and condition task number 2 performs an if-else conditional tasking, and they can all overlap with each other. This type of parallelism is almost impossible to achieve using existing task parallel programming library. Now, I'm going to show you how we can use Taskflow to program dynamic task graph to solve more complicated parallel problems. Why static task graph programming, or STGP alone, is not sufficient? In STGP, the graph structure must be known upfront before execution. That is, the execution of STGP is based on a construct and run model. You define the task graph first, and then you submit it for execution. While this is very simple to implement, it does not give you the opportunity to overlap task graph construction and task graph execution. For large task graphs, this overlap can sometimes bring a very big performance advantage. For example, here I am showing you a runtime breakdown of a task flow graph that has 10 million tasks and dependencies. Building the graph can take over 50% of the runtime, and it is typically done sequentially. On the other hand, STGP does not have the flexibility for dynamically expressing task graph parallelism. For example, depending on the values of the variables A and B, we may want a totally different task graph. Unfortunately, STGP cannot handle graph structure that dynamically depends on control flow results. To overcome these challenges, Taskflow supports dynamic task graph programming, or DTGP. Using the same graph as an example, you can create a task from a C++ lambda function object using the method silent dependent async or dependent async if you would like to acquire an additional future object that allows you to perform task-specific synchronization. When you create a dependent async task, you can specify arbitrary dependencies on previously created tasks. For example, when creating task D over here, I pass B and C as the last 2 arguments, indicating that task D cannot start until both B and C finish. More importantly, when you create a dependent async task, the runtime will start its execution immediately whenever its dependencies are met. So the task graph construction can overlap with task graph execution. One major advantage of DTGP is the flexibility for runtime-driven execution, meaning that you can flexibly assemble task graphs driven by different runtime variables and dynamic control flow results. For example, depending on the values of the variable ABC over here, I can create a different task graph. If A is true, I will create a task graph G1. If B is true, I will create a task graph G2 that runs after G1. Otherwise, I'm going to create a different task graph G3 and make it run after G1. Or, depending on the number of tasks in the graph, if G1 has 100 tasks, I'm going to run G2 right after G1. Otherwise, I will create a new task graph G3 and make G2, G3 run after G1. This type of dynamic task graph parallelism is very difficult to achieve using static task graph programming model because you cannot decide the task graph structure upfront. Now, I'm going to present some real-world applications of Taskflow. We have successfully applied Taskflow to parallelize an important application in VLSI design, that is static timing analysis or STA. Most STA algorithms require us to propagate timing values from the inputs of a circuit to its output, and the computation is very irregular. For a given circuit, we use Taskflow to derive a timing propagation task graph, where each task represents per pin propagation function and each edge represents pin-to-pin dependency. Then we run Taskflow to evaluate and report violated data path in parallel. We have implemented this task parallel propagation in an open source library called OpenTimer v2, while v1 was implemented using OpenMP to carry out the widely used levelization-based or loop parallel timing propagation algorithm. We levelize the timing graph and apply loop parallel timing propagation level by level. From the results, we can clearly see the advantage of task parallel timing propagation. Regardless of the number of CPU cores you use to run the timing analysis workload, there is always a consistent gap between task parallel and loop parallel timing propagation. That is because task parallelism allows us to more asynchronously parallelize the timing propagation without the need of level-by-level synchronization. At the time of this presentation, Taskflow has a weekly download number of 7,000 to 9,000. It has grown almost 3x over the past 5 years. We have people using Taskflow to accelerate quantum computing, bioinformatics, computer graphics, embedded system, scientific computing, and so on and so forth. In today's talk, we have understood the importance of task parallel programming. We have also introduced our task parallel programming solution, Taskflow, and show you how we can use it to program both static and dynamic task graph parallelism. Finally, we went through some real-world applications of Taskflow. Using Taskflow is extremely easy. Taskflow is a header-only library built entirely with standard C++ features only. You simply need to copy the header files of Taskflow into your project, and then you tell your compiler where to find those header files. That's it. Integrating Taskflow into your project is very, very easy. Besides, Taskflow has been evolving over the past few years to a stable programming system. It actually started in 2018 as a DARPA-sponsored research project to parallelize critical EDA applications. You can visualize the execution of your Taskflow programs by running them with the environment variable tf-enable profiler enabled, and paste the output JSON content to our web-based visualizer. This helps you understand how tasks are scheduled and executed across different threads, making it easier for you to analyze and optimize the performance of Taskflow programs. Finally, I would like to say thank you to those who are using Taskflow in their projects. Taskflow is being used by a growing number of people from both academia and industry, and we are always very open to collaboration. If you are interested in learning more about Taskflow, please check out our project website at taskflow.github.io. You can post your questions on the issue page of our GitHub repository. With that, I'm going to stop here. Thank you very much.